anyways, let's get started for today. So before we get into any juicy bits in this class, what we're going to do is I'm going to do a little bit of a primer on algorithms and complexity. So some of these things you may be already aware of. If not, you can look at this sort of like a review. Now, I'm not going to be going very in depth with the material here. However, there's many books, in fact, even some of the supplemental texts and references I've supplied have very good chapters on this topic. So this is not meant to be an in-depth dive into algorithm theory. This is meant to just give you what we necessarily need to proceed when we start talking about approximation algorithms and really motivate why we want to study these things. So at least from a complexity theoretic standpoint. So before that, I really just got to start at the basics. So in computer science, we're interested in solving computational problems. In particular, we also want to understand why maybe they're harder, or possibly how and why we might want to study certain aspects of certain problems. So we can do that from an algorithmic standpoint. So this is one of those more fundamental aspects of computer science. So I need to start off with the most basic thing, what a problem is. So we're going to be seeing two kinds of problems in this class. So I'm just going to give you an overarching idea of what a problem is, at least in a computational sense. So first, I have a problem I'm going to call pi right here. And in problem pi, I have problem instances. So imagine it looks something like this. I'm going to call x what my problem instance is. And each is going to have inputs. So these are your parameters or arguments for your input. And it's going to have a solution. So each one of these input instances is going to take on some values for your parameters or arguments. And for those assigned values, it's going to have a solution. So what do I mean by this? Just for an example, imagine this was the problem of sorting, where the input is an input array of size of, say, the arrays of like n. An input instance, so for a problem instance, would just be some array of some finite length. So for example, I can give you an array of length 3. It has numbers in it. But this is just one instance of the sorting problem. So many of these dots might be different arrays of different lengths with different numbers in them. So it's quite simple. So what usually in the exact way of solving a problem, what we would do is we would consider every one of the problem instances here, and we would try to design an algorithm such that it always solves the problem instances. So I take each one of these, my algorithm should be able to accept them and correctly produce output. So what do I mean by this? So here's kind of the big picture idea. So I have my problem instance that I get from my problem. And remember, this right here is an infinite collection of problem instances. So you think of this, so this is not finite. So this is typically assumed not to be finite. It is in fact assumed to be an infinite collection of problem instances. So in the sense that we're going to be talking about, you can't just simply run a bunch of tests to just see, hey look, is the algorithm going to work or not? You can't do that. We're going to require a bit more mathematical machinery to do these things. So this is going to be an infinite collection of problem instances. My algorithm, what it does is it takes as input the inputs of the problem instance, or sometimes I call this a input instance. So it gives the input instance to my algorithm as inputs. So it goes in here. Then my algorithm will then do some processing. It does some processing. And then it produces output. So I'm assuming these algorithms, of course, terminate in finite time. And it produces output. Generally, we're curious about the time when, in fact, where I want to check, I want to know if this is correct or not. And if they match, the solution and the output match, we say it is, in fact, correct output, right? So this shouldn't be too fancy schmancy. I'm just trying to give you a breakdown of the whole ideas here. So this is the big picture here. So when I want to solve a problem, my algorithm must be able to handle any of the input instances of any one of those instances there on my big infinite collection over there. So if it's sorting, it should be able to handle any array of finite size. If it's actually we'll talk about some problems later on, but you should hopefully get the gist of this. Now, another big piece of this that you need to talk about is input size. So you may know of input size. So each problem instance, so each one of these dots here, which is just this right here, each one of these problem instances is encoded as a string of characters. Now, we typically just assume these are bits. And keep in mind when I say bits, I mean, we're going to imagine if I took, say for example, my array. Like if I was thinking about the sorting problem. Imagine I took my array and I was able to encode it into binary. And imagine I have delimiters that kind of separate each one of the parts of the array and so on. So this would be what you would want to imagine. Each one of these problem instances, in a formal sense, is like a binary sequence that's encoding the array that I want to sort, like in that one example. But it's really just the number of characters required to encode the instance. We call that the input size. So you may be very familiar with this idea. If not, that's fine. So I just will denote that as with an x if the problem instance is called x with bars on the sides, or I'll use a function called size like that. Now, because of this, I have to be a bit particular when it comes to how we analyze. Now, I'm just going to be kind of assuming our typical kind of analysis of algorithms from an undergraduate level. So I'm going to be assuming the standard RAM model or random access machine model. So I'm going to assume that my machine is capable of reading the numbers. Say if I give you a bunch of numbers, it should be capable of reading each one of those numbers as one word be fed into the machine. So there's not going to be weird expenses for reading a number out of like an array. Like if I was sorting my integers, I should be able to read each integer in constant time. So what do I mean by this? So you just got to imagine I'm able to do this. Now remember, this is not necessarily an accurate portrayal of all situations. However, it's quite realistic for the RAM model because you can think of each one of my numbers, like in my array, if I was sorting an array of integers, that each one of those is a fixed number of bits. Just like you would if you're working in a programming language, like you had ints. Say if you have like decimals, like doubles, they all have a fixed number of bits they use to represent them. So this is actually quite fine. So there's nothing too weird theoretically with that, but it's very interesting because the machine model, in fact, is of a sufficient size to handle those word sizes. That's a theoretical assumption I'm making when I use the RAM model in this fashion. So other assumptions I'm going to make is that addition, multiplication, other arithmetic operations, those all can be done in constant time as a consequence of this. Likewise, some other things you should be aware of is that normally when we think about the input size, usually we measure it quite inaccurately. So in an undergraduate course, for example, you might normally run into the case of, say, sorting. Like if we're sorting an array of integers. Normally we measure the input size in the length of the array, right? Now, technically, if you want to get really into there, each one of those numbers can be encoded with a logarithmic, it's about a logarithmic number of bits with respect to that number. But I'm making certain machine theoretic assumptions about our analysis to allow me to say, oh, okay, well, whatever, it's not terribly important. However, it is important in certain circumstances because if, say, a number in the input, like a number, say my sorting algorithm, say one of the numbers pops up in my running time, it will matter because that number is actually being represented as some logarithmic number of bits, which in our analysis, we're assuming it's just some fixed number at some point because of our machine model. However, as we're going to see some examples later on, and in fact, you may have seen some examples of this. One example would be the zero-on knapsack problem. You may have encountered this in your undergraduate studies, possibly, where the classic dynamic programming algorithm runs in so-called pseudo-polynomial-time. Keep in mind, I'm going to describe what that means later on in the class, so don't worry if you don't know what that means. In cases like that, if say a number that's in a part of the input shows up, it's actually it's going to cause weird exponential-like behavior in terms of the running times of the algorithms. So just keep in mind that input size, the way we're going to use input size, is not necessarily going to be a pure interpretation of input size all the time. So I'll be fine with typically assuming the input size to be kind of your typical things from an undergraduate setting, like if I'm sorting an array of length and the input size is n, where I assume that each one of the numbers in the array is a constant number of bits. So hopefully that is clear for everybody. So just keep in mind, this is still true, it's just sometimes you can make certain reasonable assumptions of what the input size is. So we have to consider an appropriate measure of the input size. So in cases like that, it doesn't make a big difference because normally in sorting algorithms, you never actually pull out the number and actually start trying to use it other than for comparisons. So I check if one number is smaller than another number. Remember, under our machine model assumption, I should be able to do that comparison in constant time. However, if there are some sorting algorithms that make certain assumptions on the sizes of the numbers in them, that would be where something like this might pop up. So this is generally just the point I want to make, that just kind of say, okay, well, just be careful around this. If you're familiar with this from an undergraduate level, it's not going to be any different. So I'm trying to address some of these nuanced points involving input size. Just remember, I'll give you some examples of this actually in a little bit. So just keep that in mind. So what we're going to be interested in is the design of algorithms that run in a certain time bound. Now, you may be familiar with Big O, which I hope you will. If not, you're more than happy to ask me questions about it. But we're going to be interested in our efficient algorithms for problems. Now, you might naturally ask, okay, well, what's your definition of efficient? Because efficient can be easily regarded as something that is not quite precise. Because sometimes for certain problems, you might consider certain algorithms more efficient than other ones. Likewise, you might also consider the idea of, okay, well, what is your measure of efficient? Now, for the problems we're going to study in this class, all of them are going to be hard, typically. So I'll have a more precise way of saying that in a moment. Actually, not, maybe next lecture. But the main thing I want you to take away from this is that in those types of settings, polynomial time for the running time will be what we'll expect. So we will be interested in the design of efficient algorithms. For us, these will be polynomial time algorithms. Polynomial time algorithms. So I got to define that for you. Now, I should mention why input size really matters. So even if we're not quite measuring it precisely in terms of I'm going to take the logarithmic number of bits for each one of the numbers. That will only be really relevant when we talk about problems with numbers in it. But it's worth noting that when we talk about measuring the running time of an algorithm, we're going to normally always assume worst case. And I should mention that right here, in the worst case. That's very important. There's different types of analyses you can do. So it's going to be always in the worst case. So we're going to identify instances for which the algorithm takes the longest to terminate. Now, you should be familiar with this if you've done any type of algorithm analysis or algorithms and data structures. It's pretty standard. So, that being said, as an algorithm executes, typically that will scale with the input size. So if you pick a reasonable measure of what the input size will be, you'll find that the larger that input size gets, the longer the algorithm typically will run. So I need to motivate that, just so I can give you this definition. So here's the definition of a polynomial time algorithm. So like I said, you're probably going to be familiar with this. If not, that's cool. That's why I'm working out this with you. So it's worth noting, actually, while I'm writing this, that we're not going to be very overly formal when it comes to talk about algorithms in this class. So we're not going to be seeing very much about Turing machines in this course. Instead, I'll be adopting more of an algorithms perspective as opposed to a theory of computation perspective on how we talk about these things. So in this case, I'll be talking about a polynomial time algorithm as a deterministic that means that when I provide you each sequence, so if I have a sequence of operations, they can't all just suddenly happen in parallel all of a sudden. Each step follows one before the other one. This is in contrast to non-deterministic, which I'll talk about probably next class. So a deterministic algorithm that runs in big O of n to the c for some constant c where n is the input size. So just to be clear, I'm using n here to talk about the input size instead of x over there. Like you could technically just put this right there instead of n. I just wanted to do that to make it a little easier for you if you're looking at this at the end, because a lot of people use n for the input size. Often when we talk about number theoretic algorithms or problems involving numbers, we often use this convention. We'll run into cases where this is quite frequent. But otherwise, it's also because we tend to establish inaccurate measurements of the input size very often. But it's really worth noting that often when you have an efficient algorithm for a problem, usually this distinction doesn't really pop up a whole lot. I just want to be very careful with this. So hopefully this is all good so far. So it's worth noting that normally the problems we will consider have at best exponential time algorithms. So, that being said, we're going to talk a bit more what I mean by these types of problems in the next class. So, this is mostly just getting it set up. So next time I'll start talking about decision problems and hopefully get us into where we can actually start talking about approximation algorithms possibly after that. So anyways, have yourself a beautiful day.